So welcome back. Our next speaker, we have the pleasure to have Yuval from Zurich telling us something about large blowups.
Yeah, thanks. Thanks so much for the invitation, and thank you all for coming. So I got to visit IBS last summer, and it was a great visit. So I'm very glad that I can come back, even if it's only virtually. So yeah, today I'll be speaking about some recent joint work with António Girão and Zach Hunter about large blowups. So to get started, I just want to start with one of the classical results in extremal graph theory, the Combinatorics theorem. And I'm going to state it in a slightly unusual form. So the way I'm going to state it is that if I give you an n-vertex graph, and I promise you that it has epsilon n squared edges, then you contain a complete bipartite subgraph. So you have a copy of this complete bipartite graph, KKK, where this K is at least something. And that something is some constant times log the number of vertices divided by log of 1 over epsilon. So a few comments about this. So first of all, this result is tight up to the value of this constant. And the reason this is true is that if you take just a random graph on n vertices with epsilon n squared edges, you can easily check that it does not have a copy of KKK for a K which is of the same shape, just maybe with a different constant. Another important remark about this theorem, which is related to how you've more usually seen it, probably. So usually we have a statement of this form that I have an n-vertex graph, epsilon n squared edges. You think in your head that epsilon is fixed and n tends to infinity. But actually, this theorem, as I've written it, holds for all epsilon and all n, including if epsilon actually depends on n. So for example, if you plug in epsilon being this quantity, n to the minus the same constant divided by k, you find that every graph with that many edges contains a copy of KKK. And this is the way people usually state the Combinatorics theorem. And so it's very important that because it holds for all epsilon and all n, it not only speaks about dense graphs with quadratically many edges, which is sort of what you see here, but it actually speaks about graphs with sort of in some sense any scale of edges. So the perspective I want to take on the Combinatorics theorem has to do with blowups, which is the subject of the talk. So here's the basic definition. If I give you a graph h and an integer k, the k blowup of h is just what I get when I replace every vertex by k vertices and I replace every edge by a complete bipartite graph. So here's a picture. If I start with h being a triangle, its 3 blowup is this graph, where I replaced every vertex by 3 vertices and every edge by this k33. And so again, here's the Combinatorics theorem as I stated it on the last slide. But an equivalent way of stating it is that rather than assuming epsilon n squared edges, I'm saying epsilon n squared copies of the graph K2, which is just an edge. And then the conclusion is that before the conclusion was that I had a copy of KKK, but that's just a copy of this K blowup of an edge. So the theorem says if I have many copies of K2, I contain a large blowup of the same graph K2. So again, that's the theorem. And when I set it up like this, hopefully the question that leaps to everyone's mind is, well, what if I don't contain many copies of an edge, but I contain many copies of some other graph, H? And so this is another very well-studied question. And the first result in this direction is due to Erdős. And so here's what Erdős proved. So now I fix my favorite graph H, and let's say it has little h many vertices. Now my graph G, I'm assuming it has many copies of H, and the natural scaling before was epsilon n squared. Now the natural scaling is epsilon times n to the h, because this is n to the h is basically the number of copies of H, the maximum number of copies of H I can have in any graph on n vertices. And so again, the assumption is I have many copies of H. The conclusion will be that I have a large blowup of H, and that's indeed true. But the expression is a little different now. So now the expression for the size of the blowup is, again, some constant, now, of course, depending on H. Again, in the denominator, I have log of 1 over epsilon. But in the numerator, I have some power of log n, and that power is 1 over h minus 1. Again, that's the same theorem. And just as the simplest example, if you take a triangle, if your h is a triangle, then what this theorem says is that if my graph has a cubic number of triangles, then I can find a large blowup of the triangle, but the size of my blowup will only be square root of log n because of this exponent. So before we found a blowup of size log n, now I get square root of log n. And if you'll recall, I stressed this thing that the Kovács-Turan theorem is tight for random graphs, but this result is not tight for random graphs. So if I take a random graph with a cubic number of triangles, it actually will contain a blowup of a triangle of logarithmic size. So the square root of log n is not the behavior I see in a random graph. And there's actually a reason for this. And the reason for this is that although I've stated Erdős's theorem about graphs, it's really a theorem about hypergraphs. So in fact, Erdős's theorem says that if I have any hypergraph and it has many hyperedges, then it contains a large blowup of a hyperedge. And in this hypergraph setting, this exponent is the correct behavior. So for a random hypergraph, let's say a random 3 uniform hypergraph, this really would be the correct behavior. But if I'm just applying this to the set of triangles in a graph, the collection of triangles arising in a graph is not sort of the same as a typical 3 uniform hypergraph. And so even for a random graph, the set of triangles in it is not like a random 3 uniform hypergraph. So this discrepancy, the fact that it's not tight for a random graph, is really coming from the fact that it's not seeing the graph structure. It's really working on the level of a hypergraph. So I think it's natural to ask whether we can do better if we're really dealing with graphs. So again, this is the theorem that we saw before. And it turns out that we can do better. So this is a very important result of Nikiforov from 15 years ago. And what Nikiforov says is, again, if I have a graph which has epsilon n to the h copies of h, so as before, then I do contain a blowup of h of logarithmic size. So k is at least something times log n. So this theorem has some pros and some cons, and I've marked the pros in blue and the cons in red. So the good stuff is, as I was explaining a minute ago, we've now actually gotten the correct dependence on n. So really, this is a theorem that is seeing the graph structure and not the hypergraph structure. And in fact, Nikiforov's theorem is one of a large number of important theorems in graph theory that all say something along the lines of the triangles in a graph behave differently from a generic 3 uniform hypergraph. So another very important example is the triangle removal lemma, or the Rouget-Semrau-86-3 theorem. So the fact that we got really this correct logarithmic dependence, as opposed to the incorrect power of n, of log n, in Erdős's theorem, is because Nikiforov is really seeing the graph structure. So that's the good stuff. The bad stuff is what's written in red. So there are two sort of downsides to Nikiforov's theorem. The first one is this assumption here that n is sufficiently large. So I was stressing before that the Kovács-Turan theorem and also Erdős's theorem up here, they really work for every epsilon and every n. And that's just not true for Nikiforov's theorem, or at least his proof doesn't give that. So his proof really requires epsilon to be fixed and n to be large. So in particular, it doesn't say anything in the regime where you have like a subcubic number of triangles. Or alternatively, it doesn't say anything about a very interesting question of, how many triangles do I need to guarantee even just a constant size blowup of a triangle? Because that's just a regime where it doesn't say anything. And in fact, this is a sort of major problem. So there are a number of applications of theorems of this type that would really benefit from having a theorem like Nikiforov's, where you're allowed to let epsilon tend to 0 with n, even fairly slowly. So there's a number of applications that people are very interested in that we would be very happy if we could get such a theorem where epsilon is allowed to not be fixed. The other downside with this theorem is, I was stressing that we now got the right dependence on n. Unfortunately, the cost of that is we've gotten a worse dependence on epsilon. So in a random graph with epsilon n to the h copies of h, the size of an h blowup we'll see is of the form log n divided by log 1 over epsilon. And so as I was saying, we've gotten the log n, but you see that the dependence on epsilon is different now. So in a random graph, the dependence is logarithmic, and in Nikiforov's result, the dependence is polynomial. It's epsilon to the h. There have been a number of improvements on Nikiforov's theorem and different proofs of it, and they all improved this dependence on epsilon. So Rödl and Schacht improved the dependence to basically linear in epsilon. And then I have some joint work with Fox and Luo, where we do even a little bit better than linear. So we save some tiny thing in the exponent depending on h. But all of these results are still have a polynomial dependence on epsilon, whereas in a random graph, you have a logarithmic dependence on epsilon. And also none of these improvements touch on the sufficiently large issue that I was discussing earlier. Okay, so any questions so far? Okay, if not, let me move on. So given everything I've told you so far, there's a natural conjecture that I think presents itself. And the conjecture is that we can just overcome both of the issues that we had in Nikiforov's theorem. So the conjecture would say that I have any graph h, and I give you some graph G, which has epsilon n to the h copies of h. Then it contains a blowup of h whose size is some constant, maybe depending on h, times log n divided by log 1 over epsilon. And so the point of this conjecture is that, first of all, we got the dependence on epsilon that matches what we see in a random graph. So this bound would be tight up to the constant factor, as witnessed by a random graph. And also, the other part of the conjecture is that we're not assuming anything about epsilon being fixed and n being large. So it would work for all epsilon and all n, and thus it would also give you information about finding even blowups of constant size, where you take epsilon to decay with n. So I think actually no one has ever written this conjecture down, as far as I'm aware, although it's been in the air for a long time, because it's a very natural thing to think about. And I think the reason no one's written it down is that I'm not sure that anyone really believes that it's true. So I've talked to some experts who don't think that a result like this should be true, even for triangles. But nonetheless, I mean, it's a natural question you could ask. It's a conjecture you could make, and so you can ask, in which instances is it true? So I want to tell you about the partial progress towards this conjecture. So first of all, as we saw in the first slide, the Kováry-Sós-Turan theorem is exactly this statement in the case where the graph H is just a single edge. So the conjecture is definitely true when the graph is a single edge. Now, in fact, if you think about it a little bit, you'll see that the Kováry-Sós-Turan theorem actually gives you the same result if H is bipartite. It's some easy reduction. It's not very interesting. The entire bipartite case of this problem is somewhat degenerate. So this conjecture is at least true for bipartite H. So that's some nice partial progress. And actually, that is the only partial progress that has been on this conjecture. So this conjecture, I think people have been thinking about it for a long time, but we really don't know anything about it. So in particular, this conjecture is wide open, even for H being a triangle, which is the first case which is not bipartite. And that would be a really major breakthrough to prove this for H being a triangle. But the theorem I want to tell you about is with joint work with Girão and Hunter, is we're able to prove this conjecture for all H which are triangle free. So, this includes many graphs, of course, which are not bipartite. And so to me, this is some evidence that this conjecture is actually true. I think the reason people thought it might not be true is that we only knew it for bipartite graphs, which are sort of a degenerate case. And so the fact that it's true for triangle-free graphs suggests that it might just be true in general. But unfortunately, our techniques are nowhere close to proving this. They prove this, they're nowhere close to proving the conjecture in generality or even for a triangle. Okay, so in the remainder of the talk, I want to tell you a little bit about the proof of this theorem and why the triangle-free assumption comes in. but maybe it's a good time to pause for questions in case anyone has any questions. Okay, so let me try to show you a little bit of the proof. So again, here's the theorem we're proving. We fixed H being a triangle-free graph. And the statement is that if I have an n-vertex graph with epsilon n to the h copies of this fixed graph H, then it contains a blowup of H whose size is constant times log n divided by log 1 over epsilon. And for simplicity, I'll just focus on the case of a 5-cycle, H being a 5-cycle. This is, of course, the smallest example of a triangle-free graph, which is not bipartite. And this case really captures all of the main ideas. So again, we have a graph with epsilon n to the 5th copies of this pentagon, and we're looking for a k blowup of the pentagon of that size. So what can we do? There's some easy standard reductions that you can do. So first of all, you might as well assume that your graph G is 5-partite. And in fact, you can assume up to changing n and epsilon by constant factors. You can assume that each of these parts has size n, and that in fact, not only do we have many 5 cycles, we have epsilon n to the 5th canonical 5 cycles. And canonical just means it takes one vertex from each part, and it goes around the parts in cyclic order, as I've drawn in this picture. So that's our setup. We have a graph that looks like this. And the proof really hinges on one key lemma that I want to state slowly. So the key lemma says that I can find a subset of V1, which I'll call X1, and also subsets of V2 and V5, called Y2 and Y5, that satisfy some properties. So first of all, they're kind of big, and they're big in different scales. So this X1, its size is the size we're targeting at the end. So log n divided by log 1 over epsilon. So at the end of the day, X1 will end up being one of the 5 parts of our blowup. The Y's are substantially larger. So remember, this V2 and V5 started as n. Y2 and Y5 will be of size square root n. So they're still pretty large, but obviously we've lost a lot from n to square root n. The next condition we have is that between X1 and Y2 and between X1 and Y5, we just have a complete bipartite graph. And this will be important because, of course, our goal is to eventually build a blowup, and X1 will be one of the 5 parts of the blowup. So, of course, having these complete things is what we're looking for, basically. And the final condition is a little bit weirder, but it says that if I look between Y2, V3, V4, and Y5, I see many paths of length 4, canonical paths of length 4. Sorry, I guess length 3, paths on 4 vertices with 3 edges. And what's many, it's the number I could hope to expect, which is the size of Y2 times the size of V3 times the size of V4 times the size of Y5 times a number, and that number is epsilon to some constant. So the key lemma is that I can find such a structure. Before telling you how we find such a structure, I'll just show you why this structure is useful. So again, this is just the same picture I had on the last slide. And suppose I've found this structure. So these sets X1, Y2, Y5, with all the properties I said on the last slide. So what I'll do is I'll just throw away V1, V2, and V5 and just look at these smaller sets that I found. And now if I just forget about X1, I see the same picture I started with, basically, except I've gone from a pentagon to a path of length 3. So now I can apply the key lemma again to find a set X2 in here and a set Y3 in here, such that X2 is complete to Y3. And moreover, that in what remains, I still have many paths of length 2. And the crucial thing has to do with the size of this X2. So what's the size of this X2? Well, we saw before that the size of this X that I find is log of the size of whatever it lives in, divided by log of whatever density epsilon I had. So in this case, X2 will be size log of Y2, divided by log of the density of paths, which was epsilon to some constant. But the important thing, if you'll recall, y2 had size square root of n. And the crucial thing is that although I've lost a lot earlier, so when I shrank to y2, I shrank from something of size n to something of size square root n, and my density of copies went from epsilon to some huge power. Both of those losses are just polynomial. So when I take logs, those losses just vanish. They just get eaten up by a different constant out here. So when I repeat this lemma, my set x2 that I find is still of the same shape as the final bound that I'm looking for. And so now I can just repeat the argument. So I restrict to x2 and to y3, and I keep going, I repeat it again, and eventually I find my blowup. And because every step I only lose polynomial factors, when I take logs, all of those factors vanish, and I end up with the structure I wanted, which is a blowup of a pentagon where all the parts have size some constant times log n divided by log 1 over epsilon. Okay, so is that clear to everyone? Questions about that? Okay, so if not, let me, in the last 3 minutes, say something about the proof of the key lemma. And here I won't be able to say something super intelligent, but I want to at least try to give you an idea of how it's proved, and try to make it evident where the triangle-free assumption is coming from. So again, this is the statement of the key lemma. So we're trying to find these sets x1, y2, and y5 with all the properties we had before. And the proof is going to be some new variation on the dependent random choice method. So what are we going to do? So we're going to set some parameter s, which will end up being of this shape. What we'll do is we're going to pick a bunch of random stuff. So we're going to pick s random vertices from v1, and we're going to pick s random edges between v3 and v4. So, okay, this is something we can do. We're going to set x1 to just be the set of chosen vertices in v1. So I've defined x1. Now I need to define y2 and y5. For y2, I'm going to define y2 to be the common neighborhood in v2 of all of these vertices and all of these chosen vertices. So that's y2. And similarly, y5 is going to be the common neighborhood of the chosen vertices in v1 and the chosen vertices in v4. So, okay, I claim this works. So now let's see why it gives us the 3 properties we needed. Okay, so one property is pretty clear. So I claim the second property is immediate. So I'll put a check mark there. So indeed, we needed that x1 is complete to y2 and y5, but that's obvious because we defined y2 and y5 to be common neighborhoods of these vertices plus some other stuff. So certainly every vertex here is adjacent to every vertex here, and similarly between these 2 parts. So that's easy. The side bounds are a little harder, but they're not very hard. So certainly the size of x1 is immediate because, I mean, that's how I defined x1, is to have s vertices for this choice of s. The size of y, you need to do some computations, which I'll spare you. But this is sort of basically a fairly elementary computation. When you select random vertices in a graph and you ask how many common neighbors they have, because I'm selecting at this scale, if I choose this constant correctly, we can ensure that y2 and y5 have size at least square root n. So hopefully everyone's okay with that. The hardest property is maintaining this one, that I still have many paths of length 3 in what remains of the picture. And this is crucial to keep the induction going because I need to now repeatedly apply this key lemma for smaller and smaller graphs. And so I need to still have many copies in order to be able to run the next step of the iteration. And this is the step where the triangle freeness of H of the pentagon comes in. And so the crucial observation is that because I picked from here some vertices and from here some edges, pairs in y2 and y5 are the same as pairs of vertices that complete the picture, all of these pictures to 5 cycles. And somehow the point is that because the pentagon is triangle free, asking to complete the picture to a 5 cycle is the same as asking that you're a common neighbor of the in part 2 that you're a common neighbor of these guys and these guys, and in part 5 that you're a common neighbor of these guys and these guys. If the graph were not triangle free, we would need some other constraints that tell you whether you complete it to a copy of H. But the fact that the graph is triangle free, I mean, what we're using here is that the neighborhood of the vertex V1 in the graph is an independent set. So we have this sort of decorrelation behavior where completing to a pentagon is the same as just sort of locally completing, being adjacent here and here, and from here being adjacent here and here. Okay, so why that actually gives you this claim is still not obvious, but this is sort of at this point a fairly standard idea in dependent random choice that you can make something like this happen. So I'm going to put a check mark there, even though it's far from justified. And with that, I will end the talk. So thanks for listening.